Good evening, everyone. I am Sankar H, and welcome to this lecture live session on the computational fluid dynamics course offered on NPTEL by Professor Srinivas Jayanti. I'll be your TA for this week, and we'll go through the week 11 graded and non-graded assignments that have been posted on the SYM website. Let's start with uh, the graded assignments for the week 11. And in this week we are doing the analysis of structured and unstructured grid, and also the introduction to uh, finite volume method. So let's get started with the first question. For the case shown in figure 11.1, which is this one, which of the following statements is true? Is it first point is it is a structured grid, second is it is an unstructured grid, third is structured grid can also be used, and fourth is unstructured grid can also be used. Can anyone from the audience would like to answer? The correct answers here are this is an unstructured grid, and structured grid can also be used to study this analysis, because this is obviously not a structured grid, where a structured grid is defined as the grid lines having constant x and y values. And in an unstructured or a body fitted grid, we see that, let's take a look at this line. You can see that this does not come in a single line, whereas in fact it is collection of three different lines. So similarly, any point like this is completely not a straight line, and therefore it is not a structured grid. And the analysis of this study can be also be done using structured grid such as C line and etc. And I think this answer given in the website is a single choice, so therefore you can also use unstructured grid, but since it is already an unstructured grid that is given, this statement is actually redundant over here. So even though the fourth option is correct, uh, it is redundant over here as it is already an unstructured grid. So the correct answers are 2, 3, and 4 here. We'll move on to question number 2. Given the Dirichlet boundary condition along the curved surface and Neumann boundary condition along the diagonal of the domain, in figure 11, how many algebraic equations need to be solved simultaneously when solving a steady state or steady scalar transport equation over the entire domain? Anyone from the audience would like to answer this question before I give the final answer? Okay, to find out the number of algebraic equations that need to be solved simultaneously, we can find out the number of unknowns over here. And we can find out the number of unknowns by finding out the number of cells that are required to be solved. And each cell will be of like of this shape. And by counting the number of cells, we'll get the number of unknowns, and thereby we'll get how many equations we need to solve in order to get the solution of this. So let's start by counting the cells. We'll have 1, 2, 3, 4. 40, 41, and we have 42 cells shown over here, plus any cells that are associated with this region, if at all is needs to be considered, depending on the range at which it is discretized. Therefore, since there are 42 unknowns, we'll have to solve 42 equations simultaneously. Therefore, the correct answer is option A. Moving on to question number 3. Which of the following statements is true about the solution scheme that is shown in figure 11.1? This figure over here. Local grid refinement is possible. When the statement says local grid refinement, it means that you can increase the number of cells that are being discretized over here. Local grid coarsening is possible. That means you are decreasing the number of cells by considering this much or this much part of it together, maybe like this, maybe some other manner. But yeah, you are effectively decreasing the number of cells when you mention the local grid coarsening, and the interval at which it's being evaluated is thereby increased. And option 3 is multi-grid approach is possible, and we have seen in the previous week what the multi-grid method is or how it is used. And there where we what the multi-grid approach, we first do this on a fine grid to eliminate the short wavelength errors, and we then proceed to discretize this in a coarse grid and thereby eliminate the long wavelength errors. Which of the following statements is now true about the solution scheme? Can anyone from the audience would like to give an answer over here? Okay, the correct answer is all the three of them is possible. We can decrease the number of cells by which this is discretized, and we can also increase the number of cells. Therefore, local grid refinement and coarsening is possible. And since both of them are possible, we can use a multi-grid approach to solve or to eliminate any short and long wavelength errors associated with this in an effective manner. Therefore, all the three statements are correct. Moving on to question number 4 of the grade assignments for week 11. Which of the following statements is true about the solution of the linearized algebraic equations resulting from the discretization of a steady state scalar transport equation over the domain as shown in figure 11.1? The successive over relaxation method can be used, the ADI method can be used, the LU decomposition method can be used. And we have seen in the previous week what these methods are: the successive over relaxation, alternating direction implicit, and the LU decomposition. So, can anyone from the audience give the answer to this question? We can move on and you can give the right answer if you have any doubt. Okay, the correct answer for this question is, let me explain the answers, each of them. The successive over relaxation uses the parameter omega, which is used to optimally uh, arrive at the analysis using a mixture of Gauss-Jordan and the the Gauss-Seidel and the Jacobi iteration. And with the help of this omega parameter, we can optimally estimate the answer as compared to overestimating or underestimating in the Gauss-Seidel and Jacobi iterations. The ADI scheme splits this whatever dimension we are in into the n dimensions problem is is solved as n 1D problems. So if you have a two-dimensional problem, it is solved as two one-dimensional problems. If you have a 3D problem, it's solved as three one-dimensional problem in each step. And the LU decomposition is, we have seen, splitting up the matrix into a lower triangular matrix and an upper triangular matrix. And times x should be equal to some b. Therefore, we find out Ly is equal to b and solve u x equal to y. Therefore, we find y and x from this in this method. And for this kind of problems, since the n dimensional problem is not fixed, since the grid points are not straight, since this is an unstructured grid, the grid points here are not exactly constant x and y values, and therefore we are not able to use an ADI scheme. Therefore, second option is incorrect. But the successive over relaxation and the LU decomposition can be used effectively in solving this problem. Okay, moving on to question number 5. The transformation of an unsteady scalar transport equation into a non-orthogonal curvilinear coordinate system lead to which of the following consequences? So, a curvilinear coordinate system refers to an r theta z coordinate system, which basically has a line in z direction and a curve in r and theta directions. And when the transformation takes place from a transformation of an unsteady scalar transport equation into a curvilinear coordinate system takes place, what happens is what being asked in the question. The first option is the mathematical nature changes from hyperbolic to parabolic, and second, the cross derivative terms disappear. Which of the following is the correct answer here? Okay, let's look at the options now. Mm, uh, the mathematical nature changes from hyperbolic to parabolic. That statement is incorrect, as whatever the equation was in the xy coordinate, when we change it to an r theta z coordinate, the mathematical nature never changes, and the cross derivative terms also do not disappear. If there are any cross variate terms in the scalar transport equation, they get converted into the respective cross derivative terms in the r theta z coordinates if they exist, or if that makes sense in that system. Therefore, neither one nor two can be satisfactorily claimed for to assert the answers over here. So neither one nor two is the correct answer. Moving on, question number 6. Which of the following can be claimed as an advantage of using an unstructured grid method of solution of or a structured grid solution? So what are the advantages of an unstructured grid over a structured grid solution is what is being asked. First, ease of tackling irregular geometries. Second, ease of solution Ax equal to b after discretization. Third one, ease of grid refinement after solution. Now, which of the following do you think is the answer to the question here? So the answer here is, we know that for an unstructured grid, there are no clear x and y, constant x and y lines. Therefore, that can be used to access the domain of our in irregular geometry. As we have seen from the figure 11.1 in the earlier questions, we see that an irregular geometry such as a semicircle is effectively tackled by using the unstructured grid approach over here, whereas a structured grid approach does not cannot be done for an irregular geometry such as this. Maybe even more complex geometries may come up that makes more sense to solve it on an unstructured or body fitted grid than a structured grid. Then the second point, the ease of solution of Ax equal to B after discretization. So after discretization, it doesn't matter whether you are using a structured grid or an unstructured grid. It only matters on the method of solution, on the iterative method, such as the successive over relaxation or the alternating direction implicit, or whether it is the Gauss-Seidel or Jacobi or the conjugate gradient method. Whatever it is, the solution or the ease of solution after discretization depends only on the method of solution, not on whether an structured grid or an unstructured grid is being used. So second option does not make sense here. Third option, the ease of grid refinement after solution. We can see that a structured grid as opposed to an unstructured grid is an unstructured grid over a structured grid is easier to refine because of the way we can take our the unstructured grid. Suppose we have discretized our domain like this, and we wish to refine it. We just need to we can do it ourselves rather than focusing on how it needs to be done. This freedom of choosing how the grid refinement needs to be done is up to us. Therefore, option 3 is also the right answer here. Okay, moving on to question number 7. Consistent evaluation of fluxes in the finite volume method means. First one is at least second order accuracy in evaluation of fluxes. Second one, evaluation of fluxes at midpoints of phases. Third one, flux conservation across common phases of adjacent cells. I'll give you a minute to think about it, and if I can get an answer from you, please let me know. Okay, the correct answer here by what is meant by consistent evaluation of flux refers to the flux conservation across common faces of adjacent cells. It doesn't deal with the order of accuracy, or it doesn't deal with exactly with the evaluation of fluxes at the midpoint of faces. Now, at this point, I would ask you to think about what is meant by the flux conservation across the common faces of adjacent cells. So let's look at the differentiation of a scalar transport equation that's given by dou phi by dou t plus u dou phi by dou x is equal to 0. Now we know that this is a unsteady convection equation, convection equation of a transport property phi, and therefore we can discretize this using whatever schemes we have learned earlier and write this as phi I n plus 1 minus phi I n by delta t plus u. Let's consider this to be the ith cell and this to be the I plus first cell. Therefore, here would be the I minus 1th cell. Let's take a look at the ith cell for now. So ui times phi I minus phi I minus 1 by delta x. This is how it's discretized for an upwind scheme using forward differencing in forward differencing in time and space. Now this is for ith cell. If I do the same for the I plus first cell, how would this discretized equation be? Then it will be phi I plus 1 n plus 1 minus phi I n plus 1 by phi, terribly sorry about this. This is phi I plus 1 n by delta t minus or plus ui plus 1 into phi I plus 1 minus phi I by delta x is equal to 0. Therefore, we can say here that the flux in is equal to phi I minus 1 times ui, and the flux out is equal to ui times phi I. And therefore, from here we can say that the flux in is equal to ui plus 1 times phi I, and this is all evaluated at the nth level over here. Let's assume this is an explicit FTFS scheme, and here flux out is equal to ui plus 1 phi I plus 1. What is interesting here, if you write this form or write the equation in this form, is that the flux out at ith cell is given by ui phi I, whereas the flux in at I plus first cell is equal to ui plus 1 phi I, this one over here. Therefore, this is not conservative, and uh, and this equation, this is a property of the equation, or how we have written down the equation of this one. This is not a non-conservative form of an equation. And let us rewrite the above equation as dou phi by dou t plus dou by dou x of u phi is equal to 0. If you write it in this manner and then discretize this for the ith cell, we'll get this as phi I n plus 1 minus phi I n by delta t plus ui phi I minus ui minus 1 phi I minus 1 at nth step divided by delta t should be equal to 0. Oh, excuse me. For the I plus first cell, we'll get this as phi I plus 1 n plus 1 minus phi I plus 1 n by delta t plus ui plus 1 n phi I plus 1 n minus ui n phi I n divided by delta t is equal to 0. So when we write it in this way, we can see that the flux out at ith cell is equal to uh, ui phi I at the nth step, and flux in at I plus first cell should be equal to ui n phi I n. We can see that these both are equal, therefore this is a conservative form of the equation. So that's it, what I wanted to show regarding the flux conservation that me refers to over here. Means that the flux out at the ith cell should be equal to the flux in at the I plus 1th cell. That is what is meant by the consistent evaluation of fluxes in the finite volume method. If there are any questions, please let me know. I'll wait for a couple of minutes. Okay, we will proceed with the next question. Question number 8 regarding the Bohr-Watson algorithm for Delaunay triangulation. Which of the following statements is true about the Bohr-Watson algorithm for the Delaunay triangulation? All the boundary grids are no boundary grid nodes are inserted first. All the nodes are inserted randomly. Fewer number of triangles are produced in than in the advancing front method as compared to the uh, Delaunay triangulation. First, let's recall what the Delaunay triangulation was regarding. In the lectures, Sir had explained using the Chamfort square model how uh, we can use this to uh, create a lot of interior points and use unstructured grids for the solution of this. So in the lectures he had uh, used such a similar approach to discretize and find out the values at or use this method of discretization to find out the values. And in the Delaunay triangulation, if you recall from the lectures, is that the nodes are actually inserted very randomly, and it does not necessarily have to be the boundary grids that have to be inserted first. So option 1 is wrong. And second one is that any node can be inserted at any time. So all the nodes are inserted randomly. So second statement is correct. And fewer number of triangles are produced in the than in the advancing method. That is also wrong. It depends on the number of grid points that are being used and how the algorithm works out for the triangulation. So here only option 2 is correct, and option 1 and 3 are incorrect. Okay, moving on to question number 9. Regarding the advancing front method, the following possibility can happen during the advancing front method of triangulation. Triangles of high aspect ratios are created. Domain outside the boundary is partially or partly included during the triangulation near concave boundaries. Domain outside the boundary is partly included near convex boundaries. What is the answer here now? The correct answer here is the triangles of high aspect ratios are created, and this is because it is done. It is explained in the lecture how exactly the triangles of high aspect ratios are created. So I would suggest you to rewatch it if you have not understood. Please raise a comment in the forum. And the next two statements are in fact wrong, because the for a concave boundary domain outside is partly excluded from the concave boundaries, and same for option 3 as well. So only option 1 here is correct. Question number 10. What for the following possibility can happen during the Boyer-Watson method of triangulation? First one, triangles of high aspect ratios are created. Domain outside the boundary is partly included during triangulation near concave boundaries. Domain outside the boundary is included during triangulation near convex boundaries. So what happens here is, since the uh, here the triangles of the lower aspect ratios are created when we use the Boyer-Watson method of triangulation as compared to the advancing friend method. Therefore, when lower aspect ratios are created, we can see that if you are doing a low, uh, excuse me, if we are doing the analysis of discretization near the convex boundaries such as this, what we see is that when we triangulate, some of the part that's outside may also get involved over here, and that may be a consequence of using high triangles of higher lower aspect ratios. Whereas for advancing friend method, we don't have to worry about such a case. Therefore, option 2 is the correct answer. And regarding whether convex boundaries such as this uh, domain outside the boundary is partly included, that statement is would be wrong, because when we triangulate near the convex boundaries as shown in one of the figures 11.1, we generally tend to exclude some of the area inside the boundary rather than include whatever it is outside of it. So option 3 is also wrong. We partly tend to exclude whatever is near or inside the boundary rather than include whatever is outside the boundary for the Boyer-Watson method of triangulation.
Sir, excuse me, sir. Sir, we two only having in our class, no? I think.
Sorry?
I think we two only are there in the class, no, sir.
Yeah.
Okay, sir. Like, sir, as I am having small doubt, sir.
Okay, okay. Please go
Sir,
ahead.
like previous few classes I didn't attend, like these problem solving sessions I didn't attend. So
Okay.
can I get those videos links, sir?
It's available on the Swayam website, right?
This problem solving sections, special
Yes, yes.
classes.
Yes,
Sir,
yes.
I didn't get, sir. Like I don't know how to get those.
Okay, hold on. Let me see if I can share my screen for you.
Yeah, 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 I'll see, sir.
Is the screen visible? Please
Yes,
let
sir.
me
Yes,
know.
sir. I can see, sir. Yes, sir.
Okay, so this is the Swayam website, right?
Yes, sir.
You are able to see this
Yeah, yeah,
in
I can see those all those
there
things.
is
Yes.
a problem solving session that's given over here.
Oh, yeah. Is it?
Yeah, so you can click on this problem solving session over here, and you'll be taken to a link that showcases all the three TAs. I'm Shankar. Praveen is the TA associated for Sundays, and Kartika will be doing it on Tuesdays. So This center will be the folder or the presentation folder. That means just the slides. And
Okay,
the
sir.
YouTube video can be accessed here from any week from the previous. See, you can see that this is a recording session of the 27th of February that's done. So yeah,
Okay,
20th
okay,
of
sir.
March.
Fine,
So
fine.
you can
Thank you,
get
sir.
all the lectures over here.
Yes, sir. Yes. Sir,
Yeah, go.
problem solving sessions. Just when I'm clicking on the problem solving session,
Uh,
but it is not. I'm not able to go click.
have you signed in?
Yeah, yeah. Now I got it, sir. Now I got it, sir. Thank you, sir.
Okay. Yeah.
Exactly, I got it, sir.
All right.
Thank you, sir. Sir, sorry, sir. Hello, sir.
Yeah, yeah. Go ahead. Go ahead.
Yeah, I'm having some other work. Can I leave, sir? Like, I
Yeah,
think
yeah.
you only will be there. Just I
That's
want,
okay.
I'm
That's okay.
informed.
I'll upload these lectures anyways. So if you once you have gone through the previous week, you can start attending this week as well.
Definitely, definitely, sir. I will go through all these videos, sir.
Yeah, please
What
feel
are
free to
the
raise a question in the forum, and I'll try my best to answer them.
okay, sir. Okay, sir. Thank you, sir.
Yeah, sure.
Okay, thank you, sir. Thank you so much.
Okay. Coming back to the non-graded assignments for week 11. Or we are starting with the non-graded assignments for week 11. And the first question with reference to the figure 1a, b, and c, which of the following can be considered as a structured grid? So what we can see here is that the x coordinate along this does not change. There is no discontinuity in the x-axis or in the discrete in the lines that have been or grid lines that are shown here. Whereas here there is strict discontinuity in them. So and here in 1c what we can see is this are all again there is no discontinuity in the x lines or y lines so as shown in this figure. Therefore, the correct answer here would be 1A and 1C, and 1B would be body structured or body fitted or an unstructured grid. Correct answer is 1 and 3 here. Okay, let's move on to question number 2 for the solution of Navier-Stokes equation in irregular geometries. Which of the following grids can be used? First one is Cartesian, second one is structured, third one is unstructured. Can anyone from the audience please answer this question? So for irregular geometries, we cannot use Cartesian grid, which refers to a constant x and y lines like this, but we can use structured and unstructured grids to solve the problem in irregular geometry. So the correct answer is option 2 and 3 here. Okay, question number 3. Which of the following can be claimed as an advantage of using unstructured grid method of solution over a structured grid method? First one is ease of grid generation. Second one, ease of grid refinement. Third one, ease of solution of discretized equation. We have seen a very similar questions in the graded assignments for the week 11. Let's see if anyone wants to answer this before I give out the actual answer. Okay, the correct answer here would be again very similar to what we have discussed before, the ease of grid generation and ease of grid refinement. But the solution of discretized equations depends on the method of how you are solving, such as the successor over relaxation, or the Gauss-Seidel, or the Jacobi iteration method. Whereas the grid generation is easier for an unstructured grid, and it's easier to refine an unstructured grid over a structured grid solution. So therefore 1 and 2 would be the correct answer as come, and 3 would be wrong here. Okay, moving on to the next question. Which of the following statements is not true for when we use a structured grid for flow through a complex geometry? Body fitted grids or the unstructured grids can be used only for two-dimensional geometries. Finite different techniques cannot be used. The diagonal dominance condition of the coefficient matrix is preserved. Anyone like to answer the question? So they have asked which of the following is not true. That means which of the following is false here. So body fitted this can be used only for two-dimensional geometries is a wrong statement, uh, or is false, because body fitted grids can also be used for three-dimensional geometries as well. Finite difference techniques cannot be used. It actually can be used in the same way a finite volume method is used, but it's a little bit tricky to get the exact difference between each delta x and delta y will be changing between each grid point. Third one, the diagonal dominance of the coefficient matrix is preserved. That again will not be true, because if depending on how the discretization is happening, based on that the diagonal dominance of the coefficient matrix may or may not be preserved. Mainly because the delta x, delta y, etc. will not be the same. So therefore, the coefficient matrix will not effectively be the same, and the delta x, delta y, etc. may change depending on how the body fitted grid is done. So therefore, the correct answer is all of them are false. Therefore, the correct answer is all three of them. In fact, so all three of them are correct, are false statements. Therefore, all three of them are the correct answer. Okay, moving on to question number 5, which should be our last question for today. Which of the following statements is true? Yeah, which of the following statements is true about the transformation of the Laplace equation given by, let's say, dou square t by dou x square plus dou square t by dou y square is equal to some constant into a non-orthogonal curvilinear coordinate system. The elliptic equation remains elliptic, the elliptic equation becomes parabolic, the elliptic equation becomes hyperbolic, and the parabolic equation remains parabolic. So let's take a look at how the Laplace equation is written in the r theta or non-orthogonal curvilinear system. It becomes dou square t by dou r square plus 1 by r dou t by dou r plus 1 by r square dou square t by dou theta square is equal to 0. So we can see that the elliptic equations remains elliptic, but the other two statements are wrong. And we know that Laplace equation in in the Cartesian coordinate is in fact elliptical. So the parabolic equation, that statement over here, is itself wrong. Therefore, the correct answer is the only the first option over here. Now, I think we have come to the end of the questions that are there for week 11. If you have any questions, please feel free to ask or post in the forum. I'll be more than happy to help with the questions. Otherwise, I think that's it for the week, the lectures, the live session for today. Please let me know if I need to cover something else, or yeah. Thank you for your attention, and that's it from my side.